Welcome, everyone. My name is Jeff Bryan from the Volpe Center, part of USDOT. I'm your host of this Railroad 101 seminar, Basic Operations. I'd like to introduce Dick Cogswell, engineer with FRA. Dick will be our main presenter.
Greetings, everyone.
Also like to introduce Jared Fidrzikowski of the Volpe Center, who will co-present with us.
Hello.
All right, Dick. Railroad 101's webinar series is intended to impart to those who are planning and designing railroad infrastructure and service some fundamentals regarding four primary topics. We have four webinars: train types, track configuration, basic operations, and signal systems. So what's the focus of this webinar, Basic Operations?
Well, hopefully this webinar will answer commonly asked questions about railroad operations. We will start with operational goals and then focus on the capacity of the railroad, what it is, how it is productively used, how capacity can be lost, and finally tools for managing capacity while introducing new service.
All right. Well, Jared, could you talk about the operational goals to start?
Sure. The operational goals listed are minimize trip times, run a cost-effective operation, respond to customer needs for reliability and flexibility, and accommodate track and signal maintenance.
These goals apply to both passenger and freight, and capacity is key to achieving all of the goals.
So, railroad capacity. Jared, let's talk about the two definitions.
Physical capacity is the maximum number of trains that can physically fit and travel the route. Practical capacity is the number of trains that can be accommodated with an acceptable transit time.
Capacity is about available space and time. In trying to manage capacity, whether one is a planner or a dispatcher, the challenges include balancing trains throughout the day, accommodating maintenance and inspections, and dealing with operational irregularities and anomalies, all while keeping acceptable transit times for the various trains.
So, Dick, to manage railroad capacity, we usually think about things like how is the capacity used, how can we make the best use of it, how do we know when it's necessary to increase it. Are there any overarching comments that you think would be helpful for our listeners?
Well, the way to best use the existing capacity is to optimize the relationship between infrastructure and operations. We will first show a number of examples of the productive use of capacity by trains and maintenance, and then we will show how capacity is really consumed by suboptimal infrastructure, deterioration, breakdowns, and lack of planning for operations. In the Train Types and Performance webinar, we of course recognize trains as the prime user of the railroad. We discussed how it is critical to keep in mind the characteristic movements of the various trains in order to optimize the use of railroad space and time.
And I'll recap the train types and their characteristics. Let's start with local freights. They travel between 5 and 10 miles per hour and have the lowest priority on the railroad. They can consume massive amounts of railroad capacity because of their slow speeds and frequent stops at industrial sites just off the main line. Tonnage trains usually travel from a single origin to a single destination. Even though their speed averages between 20 and 30 miles per hour, because they carry heavy loads, braking can be difficult. They are not particularly time sensitive. A few hours late is okay. Manifest trains pick up groupings of cars at distribution yards. They travel between 30 and 40 miles per hour and carry a variety of cargo, some of which may be time sensitive. Intermodal trains travel at an average of 50 miles per hour. They are the fastest, highest priority freight trains. Compared with other freight trains, intermodal cargo is lighter weight, higher value, traveling farther, and on tighter schedules. And now for the passenger train types. Because of frequent station stops, commuter trains travel at a rather low average speed, 30 to 45 miles per hour. In peak periods, commuter trains use a lot of railroad capacity due to their frequency. Intercity passenger rail trains, by definition, connect two or more metropolitan areas. This category includes four train types. Long-haul trains like Chicago to LA, which has a low time sensitivity, an hour late is not unusual. Short-haul trains like Washington to Baltimore, which are time sensitive. Higher speed trains like Acela from Washington to Boston, maximum of 150 miles per hour, which are very time sensitive. And high speed like the Future California High Speed Rail from San Francisco to LA, which is over 200 miles per hour maximum, which is extremely time sensitive.
All right, thanks. Well, let's move on now to another use, which is railroad inspection.
Track inspections per 49 CFR parts 213.233 is driven by the class and type of track and whether the track carries freight or passenger or both. Mainline tracks carrying passenger trains are required to be inspected twice weekly via high rail cars, like the ones shown on the slide. Tracks higher than Class 5 require track geometry checks and other types of checks. Suffice it to say that on the main lines, the inspection via a high rail truck at 10 miles an hour takes a lot of railroad capacity. And if something needs to be fixed, even more time is consumed. And of course, inspections take place during daylight hours, which is prime time for train movements, especially passenger trains.
So, and the last part of using capacity, we're going to talk about railroad maintenance.
Note that heavy maintenance, such as tie and rail replacement, or work requiring large on-track equipment, typically is scheduled for 8 hours of uninterrupted time. Double-track maintenance requires worker protection, flagmen, and horns to clear the track being maintained, while a train moves on the other track. Maintenance on a single-track railroad usually takes the track out of service completely.
Well, thanks, Dick. Now let's talk about consuming capacity, which is the less productive, inefficient uses of railroad capacity. All right, first up is an example of single-sided platform consuming capacity.
Okay, we see the negative operational effects of this situation on many corridors. A single-sided station platform can change the whole traffic pattern, especially with commuter rail, because of the frequency of the headways, and the operational effects can be huge. In the diagram shown, an inbound commuter train in the morning peak is on its way to a major urban area. The commuter train has to cross over to access the platform. All the inbound and intercity trains have to follow, and this, of course, is on a double-track railroad. Meanwhile, outbound trains wait to make the crossover move in the other direction.
How can we make better use of the existing capacity?
Simply installing a platform on both tracks at the station is the obvious answer. This is a relatively inexpensive improvement that benefits all traffic on the corridor.
And our second example is about platforms that are shorter than the train.
Certainly, when the train is longer than the platform, passengers have to move to the front of the train to exit, or whatever doors are open. And boarding is also more bunched on the platform. This all produces longer dwell times as a result. If the station is on the main line, longer dwell times become delays for all the traffic on the main line.
All right, and this is the third example here. We have suboptimal infrastructure conditions, and we talked about that in the track configuration webinar.
Yes, each condition slows train speeds on the main line. As we discussed in the track configuration webinar, remedies include adding bidirectional signals and signalizing passenger tracks at an appropriate spacing.
So here are two examples about parking on the main line. What's that about?
Yes, in both of these cases, the main line is essentially used as a rest stop. The first is caused by the absence of a holding area. As an example, at a transfer point like Chicago, if you have unit coal trains coming from the west and the cars are to be transferred to another railroad and the receiving company is not ready to take the cars can be parked on the main line.
Doesn't this mean that one of the mains in the double-track railroad is out of service?
You got it. Construction of holding areas or yards takes acreage and money, but it can save a lot of railroad capacity. The second example of parking on the main line is caused by the absence of a turnback track. In many corridors, we see commuter trains, especially zone express commuter trains, turning back on the main line.
And with Commuter Express, this can happen 6 or so times in a peak period at both ends of the line?
Yes, the negative operational effects on the traffic on the main lines are huge. The remedy, of course, is to install a separate turnback track or spurs so that the train can change direction off the main line without parking on the main line.
All right, we're going to talk about a new category of consuming capacity, and this is around deteriorations and breakdowns.
Okay, this slide shows an example of track deterioration. Track defects are a leading cause of train accidents, and when accidents happen, railroad capacity is definitely consumed.
The example shown is track buckling. The Volpe Center's 2003 research showed an average of 38 derailments per year due to buckled track.
Inspection and maintenance are the only ways to keep track deterioration in check. What is particularly disturbing about buckled track is that the signal system will not detect the buckling. The rails still conduct the electrical energy in the track circuits, so there is no signal warning for an oncoming train of the conditions ahead of it.
So we can also lose capacity from failures in the train equipment itself.
Consider this example. During peak periods, the Hudson River tunnel carried 40 to 45,000 travelers per hour. In January 2014, commuters were stranded on a train that lost power and stopped in the tunnel because of a broken catenary wire.
And Dick, what's an example of a train control failure?
Well, we had a recent example of a lightning strike that hit a central instrument house of a major interlocking at a junction outside of Boston. The thousands of wires inside the house became a fused mess of copper, causing a massive slowdown of all trains. This was a particularly bad incident. Lightning strikes during summer thunderstorms happen rather frequently on radio towers that dispatchers use to remotely control switches or hit the track circuits.
All right, so now we have the last category of consuming capacity, and that's the lack of planning for operations.
Many problems occur because of the lack of planning. Planning does not solve everything, but it can go a long way to avoid unproductive consumption of railroad capacity. Introducing passenger service on existing freight routes means introducing a uniform schedule into a non-uniform schedule freight world. A disciplined approach is required to ensure the passenger trains run on time. Freight varies greatly by day of week and weight of train. Class 1 railroads adhere to a certain amount of scheduling because they have to balance locomotives and crew moves. But Class 2 regional railroads and Class 3 short lines often ignore the benefits that scheduling could bring. The mindset has been, it will get there when it gets there.
Thanks, Dick. Well, now we're going to move on to how to manage capacity. And what are the building blocks and tools we're going to use?
Well, to move towards a more disciplined approach to operations, we will talk about developing a schedule. Then we will touch on TPC, or Train Performance Calculator modeling of a single train, and RTC, or Rail Traffic Controller modeling of all the train traffic on a corridor. For planners and engineers who are developing new service, the schedule, the TPC, and the RTC are important tools. To start, however, let's look at the aspects that make up train transit time.
What is train transit time?
Train transit time is the time a train or trains can reasonably expect to travel a certain route given various factors such as the type of the train, the minimum run time or free running time, stopping distances, slowing or speed restrictions, and other expected delays over the route. When considering all trains together in a corridor, transit time becomes a function of the number and kinds of trains on the corridor, their speeds, their stopping patterns, priorities, whether they have a uniform or non-uniform schedule, how they interact with other trains, which includes the train densities, potential anomalies, headways, overtake, crew time limits.
All right, thanks. So let's start with the headways. What is a headway? How can planners and engineers use headways to make efficient use of the railroad capacity?
A headway is the time between two successive trains operating on a railroad. An ideal headway is the time between trains that is required to avoid signal restrictions without hitting a yellow signal or a red signal that would slow them down or cause them to stop. As a general rule, closer spacing of signals permits more trains in a set period of time. So closer spacing of signals is a way to increase capacity. But of course, you still have to provide for the worst case braking train distance out there to set the block length.
All right, let's now move on to overtakes and meets.
This diagram shows a passenger train overtaking a freight train. The freight train moves into the passing track.
Planners and designers have to identify where it would be efficient for a passenger train to overtake a freight, don't they?
Yes, a good example would be from San Antonio to Houston. This is a 200-mile long route for a passenger train with no intermediate station stops. As the passenger trains typically run at 79 miles an hour on this route, this is a good candidate location for overtaking freight trains.
All right, so this diagram shows meets where the lines are crossing. And Dick, why is this called a best case scenario?
Well, this diagram shows a best case condition. Trains are running in opposite directions at exactly the same speed and able to pass each other without delays at the appropriate passing tracks. They take turns using the passing tracks. In reality, trains do not operate at the same speeds because of constraints from grades, temporary speed restrictions, inefficient siding placements, and passenger station stops.
All right, so here we're going to show the real world of delays.
Yes, with a single track railroad, overtakes are common. When you also have to have meets, this can be challenging. In the diagram, train A and C will meet. Also, C is overtaking B. Consider that even if the railroad has signalized passing tracks every 10 miles, if they are occupied to allow overtakes, the meets can occur only at every other passing track, that is, every 20 miles.
This slide shows the delay experienced by train A because of the time required for trains B and C to pass through. While train C may go 90 miles per hour, train B, the freight train, may only be traveling at 30 miles per hour.
This is the time dimension that dispatchers and planners need to consider.
Let's look at train interaction and train speeds and stopping patterns.
This graphic shows a ranking of the average effective speeds of trains from high-speed passenger trains to the slowest local freight trains. The pattern of dots for each type of train represents how often and how long they stop. Compare the stopping patterns. Local commuter and local freights obviously have lots of intermediate stops. High-speed rail and intermodal freights have typically more end-to-end stops.
This speed and stopping info are key inputs to dispatchers' strategies to keep trains moving along, aren't they?
Yes, absolutely. And for those planning new services, they are key inputs to the development of schedules and model runs.
All right, Dick and Jared, could you explain this table of expected speeds given various densities of freight traffic?
These are sort of rules of thumb for corridors with heavy, medium, and light freight traffic. In corridors with very heavy freight traffic, like the CSX corridor from Buffalo to Albany with 40 to 60 or more freight trains per day, the passenger trains may not be able to run at their highest efficiency. If they achieve an average speed of 60 miles an hour, that is pretty good. In the design of track and signals, priority should be given to the freight trains.
In medium freight traffic, with 10 to 20 freight trains per day, the designer would try to achieve good efficiency for both passenger and freight and expect a 60 mile per hour average speed for passenger trains.
In light freight traffic, with only 1 to 4 freight trains per day, the design of the signals and track would normally give priority to the passenger trains, and an average speed of 70 miles an hour would be reasonably expected.
Well, thanks. So we also have to consider the crew on-duty limit, which is 12 hours. How does the on-duty limits affect the management of the railroad capacity?
Well, the crew limits can affect railroad capacity when problems crop up and things take longer than expected. As an example, if a freight train blows an air hose somewhere, the train comes to a stop. It can take up to 90 minutes or so to find and fix the problem because somebody has to walk the train to find it. Given this delay, the crew may now not get to its destination before the 12-hour time limit expires. And if the train can't even make it to a crew change point, which is typically a major stop like Richmond, Virginia, the train stops out in the countryside. While a new crew is brought out, the train is sitting on the main line, tying up railroad capacity, and nobody is moving.
So putting all these factors associated with the train transit time together, how does one begin making a schedule?
Well, there are basically two approaches. For an existing, heavily used freight line to which passenger service will be added, you can start by documenting the average number of freight trains, estimate their departure times from major terminals and yards, and build in delays. Then add in the passenger service.
Can't you also start with the passenger trains?
Yes, but this is more commonly done in a light-density freight environment. That can be a good way to start. Once the passenger trains are set, add the freight trains and related considerations, then estimate delays. Then fine-tune the station dwell times. Typically for passenger convenience, trains leave stations in the morning after 6 a.m. and hopefully arrive before midnight. People just don't like getting on trains before 6 a.m. or after midnight.
So we also have tools, which you had mentioned before, but how do the modeling and simulation tools help with managing capacities?
Well, these tools, the simulation tools, bring time and space together. The TPC, or Train Performance Calculator, models one train at a time, taking into account various speeds, grades, braking distances, station dwell times, etc. It does not factor in other traffic. It will give you a perfect running time. For that reason and others, TPC results are too perfect. FRA typically requires at least a 7% pad be added to the TPC results. You can check the FRA website, the 2005 Guidance Manual for Rail Corridor Transportation Plans, for more information on the 7%. The RTC Rail Traffic Controller model produces graphics like the one shown above, in which all trains are together. The inputs to this model include the signal system, train priorities, temporary slow orders, typical dispatcher decisions regarding meets and overtakes. The RTC string line chart graphics are helpful to understand where infrastructure changes are needed and where service windows exist. The RTC model output is delay minutes per train type for all trains on the corridor, shown through the horizontal lines. Adding new service, for example, 2 or more passenger trains per day, could increase the delays. Adding passing tracks or making other adjustments to the infrastructure could reduce these delays.
All right, Dick. So I thank you for all that. I can see that this is a very complicated topic. How would you sum up what we've just talked about today?
It is complicated. In the meantime, we would encourage planners and engineers working on projects to think like a dispatcher. Take stock of what is out there, how each train moves, and the time it takes for each move. Remember, the dispatcher lives in Einstein's fourth dimension. Time, time, time. He doesn't care about distance. It's a juggling act that he has to put up with.
Well, thank you very much, Dick and Jared, and all of you. That's it for the Basic Operations webinar. To review this or any of the other webinars, see the Rail Network Development, the Oversight Guidance page at fra.dot.gov.